Hi, everyone. Thanks for coming. Today we have Daniel Platt, who'll talk about convolutions and manifolds and applications to geometric deep learning. So you have about 50 minutes, and then hopefully, if the room is still yours, where you're in right now, then we'll have some questions.
Okay, yeah, that sounds very good.
Mm-hmm.
Thank you very much for the invitation to the organizers. Very happy to speak here. So today is a bit about machine learning, a bit about geometry. The first 10 minutes will be an intro to some basic machine learning stuff, which doesn't have much to do with geometry. And then we move on to the geometric stuff. And of course, you're most welcome to always ask any questions. That would be very nice if you could interrupt a bit sometimes. Right, so let's get started. First thing is, what's a neural network? So the whole point is, if you have some data, input X, some output Y, then you want to find some function which approximates that. Ideally, the function, if you input X, should give you Y. That may not always be possible. For example, if you have some stochastic data, there can be the same input leading to different outputs. So it may not be possible to perfectly match this data, but you want to approximate it as well as possible. And so what that means to approximate it as good as possible, it means this. You choose some family of functions from Rn to R, parameterized somehow by some parameters, theta. And then you want to find the best parameter in the following sense. You want to minimize this error. So you always compare f of x minus what would be supposed to be the output of your function f. And then you square all these errors, sum them all up, and that's the error of theta, and you want to minimize this. And so in reality, I will explain one particular family of functions f theta in a second. In reality, the problem of finding this minimizer theta is really hard. But for the purpose of this talk, let's just pretend we have some magic algorithm which always gives us the unique absolute minimizer theta of this error, because then it's still an interesting problem to find good families f theta. So that's basically the whole point of the talk. How would you want to parameterize such functions? And so the easiest, or maybe not the easiest, but one easy way to do it are fully connected neural networks. So you parameterize your f theta as follows. You take a composition, you compose a bunch of linear maps, L1, L2, L3, and so on. But every other map is sigma, which is not linear. But actually, so I said linear and I wrote affine, so it's always a matrix multiplication plus a vector. So affine is the better word. And so the point of having these non-linear maps sigma is, well, if you didn't have it, you would just have a composition of a bunch of affine maps. So in the end, that would again give you an affine map. So you would just have found a really complicated way to parameterize an affine map. So that's not very useful. But it turns out, if you always take affine map and then this not affine sigma and so on, then you can actually approximate really complicated relationships between x and y. And so it doesn't matter for the rest of that talk, but just so that you know, like there are a bunch of choices for sigma, and one choice that you could have in mind, for example, is take the sigmoid function, which is a logistic function, and you just apply it to each component of your vector all the time. So for example, here on the right, our input, our x's live in R4. You do this matrix multiplication, you add a vector, you apply the sigma, you get something in R3. Then you do the same thing again, you get something in R. And then we can count how many parameters there are. For this matrix, there are 12, there are 3 here, another 3 parameters, 1 here. So you can calculate how many there are in total. I'm not going to try now. And you can imagine if you have like very high dimensional input data, but there are lots of parameters. And actually that's one of the main drawbacks of these fully connected neural networks. So you can imagine maybe your input are some images, maybe 1,000 pixel times 1,000 pixel images. And so the grayscale value of each pixel is represented by one real number. Then you have 1 million input thingies. And if your next layer should be 100 dimensional, then you already have 100 million parameters. It's very difficult to minimize over such a big space of parameters. So that's the thing people dislike about neural networks, and that's why they came up with convolutional neural networks. So here's what convolutional neural networks are. So before I say what a network is, let me remind you of what a convolution is. So if you have two functions on Rn, let's say compactly supported, so that this integral makes sense. But let's not worry about this, so a bunch of functions. Then we define f star g at a point x via this integral. Now this is what computer scientists call a convolution. Mathematicians would want to have a minus sign here. And if there's a plus sign, they would probably want to call it a correlation. But yeah, I mean, that's life. So for today, we just call this thing as it's written there, convolution. And the point of that is, or one of the interesting properties of these convolutions is, if you start with something non-smooth, like this f here, very spiky, and you convolve it with something smooth, so I convolved it with a smooth bump function here, then you end up with a smoothed out version of your non-smooth f. But I mean, that's just like some mathematics so far. And now for machine learning, they kind of invented a discrete version of that. So let me tell you how that's defined.
Sorry, Daniel, can I ask a question?
Yes.
I mean, why do you actually need a plus sign? I mean, is there like, why not like the normal minus sign?
I need the plus sign for this for this statement in the lemma here to be true later. Because I took
just technical assumption.
I mean, right now, I don't need it at all. It's just that all the other convolutions that I'll define, they're taken from the computer science literature. And they're always mimicking this definition here with a plus.
Okay, then.
I think it doesn't really matter because you can make a change of variables and then you replace f by f composed with minus multiplication by minus 1.
Yes, that's one way to say it. Another way to say it is like these things with which we convolve, this what's called theta here. I mean, this is parameterized anyway, so you can, yeah, instead of convolving in the plus fashion with theta, you can convolve in the minus fashion with the opposite of theta, if you want.
I see. Thanks.
Yeah, but thank you for the question. Very good question. Any other questions or comments about this stuff so far?
It's that VW in the formula, right?
Sorry, in which formula?
It's theta VW.
Oh, this here?
No, in the sum. Right, it does depend on like.
Yes, you're right. Thank you. Yeah. Okay, so let's ignore the formula for a second. I mean, probably you should ignore it all the time because there's an arrow. But let's look at the picture first. So you take an n by n matrix as an input, and I said 3 by 3, but you can choose other matrix sizes if you wanted. And then you convolve these two, and the way you do it is as follows. You take your little matrix, the 3 by 3 matrix, and if, for example, you want to compute this blue square here in your output matrix, take your little matrix and put it on top of your input matrix, and then multiply the numbers which are on top of each other. So you multiply this 1 with this 0, you multiply this 3 with this 0, and so on and so on. And you sum them all up, and that's how you get 23/9 for this blue square in the output. And I mean, one small detail, if you, for example, wanted to compute the very top left corner of your output, and you put your little matrix over your big matrix, then it overlaps. So like the little matrix covers some stuff where the big matrix has no entries, and then we just take them to be 0. So that's not made precise here in this formula, but and so the formula should just model this picture that I just explained, but these indices are wrong, and I mean, I won't bet my life on those indices here. And so, yeah.
Is it just the convolution on the group Z2?
Yes.
Okay.
And so these two things are related as follows. I mean, there are many things you could say how they're related, but one thing is the following. If we define the map dis for discretization, it takes a function on the unit square and gives you an m by n matrix by just evaluating this function at a bunch of points. Then you can do two things. Either you convolve your two functions first and then you discretize, or you discretize your two functions first and then you use this funny convolution here. And the statement is, well, these are both matrices of size m times m, and if you fix one entry, then the difference converges to 0 as m goes to infinity. And okay, but I later decided I want to skip the proof, so let's ignore the proof. But yeah, I mean that's how you go from smooth to discrete, and that's how these two convolutions are related. Good. I think yeah, that's good. And there's one last thing I want to say about like this standard machine learning, and that is yeah, maybe something to spark your enthusiasm for machine learning. You can now combine these fully connected neural networks and convolutional neural networks, as you see here. I have a bunch of convolutions, C1 to CK, and then always these linear things and these sigmas. And you can make very complicated functions with very many parameters this way. So one example you see here in this picture, it has two convolution layers. Let's ignore what subsampling is. And 3 fully connected layers. Gaussian connection also means fully connected. And that was the thing that made these convolutional neural networks popular. That's the original, but that's the architecture from the original publication of Jan LeCun. And yeah, if you have such a neural network with loads of layers, you can still write down the same formula for the error of theta, and you minimize over theta, and then you get some approximation. Okay, I mean, this picture also totally unimportant for the rest of the talk. Okay, but so far, does that make sense about neural networks, everyone? That was the
Can you ask you a question?
Primer. Yeah.
So before that, when we had just normal neural networks, we had like you have an affine map, and then you apply some sigma, and then you go by affine map again, then you apply the sigma as well, and so on and so forth. And the convolution is defined, on the other hand, for like you need to take two matrices of two arbitrary square matrices. But here, if you start with some like higher dimensional space, what does it mean to apply a convolution like C1 and C2 and so on and so forth? It's not like a matrix, is it? I don't really understand how you can start with convolutions and then to proceed with a normal neural network.
Right. So the input of C1 would be a matrix.
Okay.
And the output is a matrix again.
Mm-hmm.
That's the thing from the previous slide. And
I see.
so at the end of CK, you have a matrix.
Mm-hmm.
Right. But now you asked the right question. I said, oh, well, these fully connected guys, they take a vector, they don't take a matrix.
Well, I mean, yeah, I see.
But what happens is just you forget about the matrix structure and just treat it as a vector.
Mm-hmm. Mm-hmm. I see. So you start with.
Yeah, sorry.
Yeah. So the point is that you start with a matrix and then you forget about it.
Yes.
I see. Thanks.
Yeah, but thank you for the question. Good thing to point out. Yeah, and so in this example here, you start with an image, and that comes with a natural matrix structure. And then it's exactly at this point here, after all these convolutions, that you forget about the matrix structure. Right.
Why do we apply this convolution? Is some sort of like we're reducing the noise or something like that?
We're reducing the noise, you say?
Yeah. Is it why we apply convolutions, or like why do we want to add these convolutions?
I mean, there are some reasons. So one reason that's related to reduce the noises, maybe you want to reduce the resolution of your input picture. Like it's really high dimensional in the beginning and you want to make it smaller, which I didn't explain how that works, but you can imagine if you move your little matrix, not just by one step, but by 2 steps or so, you downscale your picture. But I think that like the main reason is just you somehow want to make use of all the input, but you can't do a fully connected network because that would be too many parameters to optimize over. So you must do something, and that's like the obvious thing that people came up with.
Okay.
Yeah. It's what is true is if your little matrix, if you fix it, maybe so you say 1 1 1 1 1 1 1 1, and then you apply it, that means you reduce the noise in your picture. But yeah, I mean, in our case, these filters are learnable. So in the end, it can be some crazy numbers. It can be 10 minus 10, 0, 0, 0, 0, 5 or so. And then it does some crazy thing, but definitely not reduce noise. But yeah, thanks for asking that. Okay, so then let's crack on with some geometry, or I mean, let's introduce a bit of geometry at least. The problem is the following. Suppose you have a bunch of points in a manifold, and like I'm only talking about surfaces here, but all of this generalizes to higher dimensional manifolds. And then you have the following data. You have input x, which are maps from your set of points to the real numbers, and outputs which are just real numbers. And now you want to find an interesting family of functions to minimize over to approximate these guys. And one thing you can do if you want is you identify maps p comma r with r to the n, which you can do because a map from p to r is just a real number at every point. And you forget that they were living on a manifold or something, and then you just use a fully connected neural network. But you can't use a convolutional neural network because there is no matrix structure. And I mean, it's also, there's no good motivation how you could define maybe a more clever convolutional neural network, because if you take 2 functions on a manifold, there is no natural convolution for an arbitrary manifold. If you have a group structure on your manifold, like if you have a Lie group, then you can define a smooth convolution, and this can inspire the definition of a CNN. But yeah, I mean, in general, you don't have that. So there are there are many solutions. This is a problem that many people have thought about, and they came up with many different things. And I'll present 2 things, which is not original work by me, but from these references here. Oops. And the first solution is, well, turn your point cloud into a graph. So for example, you say, oh, add an edge between every 2 points with distance less than 1 or something like that. This way you get a graph, and then you can apply spectral graph convolution. So that's going to be the first thing I explain in a second. And that's a bit better than forgetting about the manifold structure altogether, but you can still do something a bit more clever, because if you move from a manifold to a graph, you're still forgetting about quite a lot of the structure that's there. an even nicer thing to do is, well, if you have, say, a function f on your manifold, you can convolve it with a function g on R2 by this definition. So you say f star g equals, and then some integral over the tangent space at the point x. So you can pull back your function f by the exponential map. That's then a perfectly well-defined function on the tangent space. And then you have to make some choice. If you choose some identification of R2 with your tangent space, then your map G is defined on the tangent space, and you can multiply them and integrate them. But the problem is, of course, I must make some choice of identification, and there is no canonical choice. So as it's written, this thing is not well defined. And gauge equivariant convolutions are one way to make this expression well defined. So those are the two things that I'll explain in the rest of the talk. So let's start with the spectral graph convolution. So suppose you have a graph G with edges and vertices, and you label your vertices V1 to Vk. Then there are two matrices you can cook up. The first is the adjacency matrix, which is 1 if two vertices are connected and 0 otherwise, and the degree matrix, which is just the diagonal matrix of all the degrees. So here in this example, you see this little square graph with 4 vertices, and I wrote down for you the adjacency matrix and the degree matrix. And then you can make this definition. You can define your delta to be d minus a. So that's still some k times k matrix. And that's called a Laplacian. And so, I mean, you totally wouldn't need to care about this, but just maybe for interest, why is it called a Laplacian? You do know the smooth Laplacian on Riemannian manifolds, but what do the two things have to do with each other? Well, you can draw many parallels, but one theorem that I found nice is the following. If your graph is embedded in the manifold, then you have that the spectrum of the graph Laplacian converges to the spectrum of the smooth Laplacian as the number of vertices tends to infinity. But now, I mean, first, like making it precise, what does it mean? One spectrum converges to another spectrum is hard. But even then, it's not quite true, because if you choose a really dumb graph, like all clustered in one part of the manifold, it's not going to see anything about the spectrum of the smooth Laplacian. So what this statement actually says is, if you choose a graph randomly, then with probability 1, this complicated to define convergence holds. So it's a really hard to state theorem. But we won't need it, but just if you're curious about it, you can look that up.
Sorry, can I have a question about it?
Yes.
Isn't it enough that, like, if you want your K graph to be 1 over K net in your manifold, will that suffice? Or like,
can you repeat the question?
Let's say that your K graph is 1 over K net in your manifold. Like,
yeah, okay.
Yeah, well,
let's assume that.
Yeah, well, wouldn't it suffice to say that the spectrum?
Oh, well, yeah, I mean, in this case, you will have that the spectrum of the graph Laplacian converges to the spectrum of the smooth Laplacian. But
okay.
I mean, you still have to say what it means for a spectrum converge, like for two sets to converge to each other.
Yeah, okay.
But yeah, true, it removes some of the difficulty from stating the theorem. Yeah.
Sorry, what is a net?
Yeah, I mean,
like every point is a distance less than epsilon from some vertex.
Okay, yeah.
well, I mean, yeah, but you must also fix some minimum distance between vertices. Otherwise, you can have a million points clustered like just on one point. Okay, I mean, you can make that theorem precise, but let's not do it. Let's forget about this whole thing with smooth manifolds. We really don't need them right now. But what we do need is the following. So we have our delta, and one can check that it's a symmetric and positive semi-definite matrix. So as such, it has an orthonormal basis of eigenvectors, T1 to Tn, Tk. So in this case of this little square graph here, the eigenvalues are 0, 2, 2, and 4, and these eigenvectors are written here. And what you can notice in this case, for example, is you can compare this with the standard Fourier basis on T2. So these things, e to the 2 pi I, blah, blah, blah. If you take the real part of these functions and then like discretize it to a 2 by 2 matrix, as I've done before, then they actually agree with these eigenvectors of delta. Yeah, but that's just an aside. But the thing is, if you have, now that you have your orthonormal basis, you can uniquely decompose every vector in Rk. So for example, we write f as Cm of f times Tm. So Cm is always the mth coefficient. And then you can define a convolution of two functions, of two vectors, f and g. So those are vectors in Rk. But if you want, you can think of these vectors as functions from your vertices into the real numbers. And the convolution is defined like this. You exactly multiply the coefficients with each other. And if you want, you can take that as a definition of convolution for on the torus, for example. There's an eigenbasis of the Laplacian, and you can multiply the coefficients of these eigenfunctions. And that gives you the same thing as I've written down in the beginning. Okay, and then that's basically it. So how you define your spectral graph convolution is now using this formula. So we have k eigenvectors. If you have a big graph, there can be a lot of them, maybe 1,000 or something, and you don't want so many parameters. So what you do is fix some number which is less than k, and choose some parameters theta. Then the convolution of x and theta is just the same formula as before, but you stop after the dth eigenvector. Yeah, that's the spectral graph convolution. And maybe just one note, what does that have to do with the smooth convolution is if G is a uniform grid on a torus, then there exists some eigenbasis B of delta such that this equation is, or this statement is true. Convolve first and discretize later is pretty much the same as discretizing first and then convolving with respect to this basis B. But now that you see the statement of this lemma, you may be a bit shocked, because when I wrote down this formula for the convolution, I made it seem as if it's independent of the choice of basis, but it really is not. Like it very much depends. So if you choose a dumb basis, this statement is no longer true. And yeah, one example where you can see it fail are these pictures on the bottom. So let's not dwell on them too much. Yeah, okay, but any question about the spectral graph convolution? I think that's what I had to say about this spectral stuff.
Does the lemma not depend on the choice, so that works for any D?
Oh, okay, fair enough. That's a good question. No, it only works for d equals to k, which is a bit stupid because I just said d less than k, but yeah, good point.
Yeah, you could probably choose something like k minus 1, but it should grow like k, I guess, and not be fixed.
Yes. Yeah, but I mean, this I don't know if that statement that you said is true. I mean, probably it is, but I only know the proof for the case d equals to k.
Fair enough.
Yeah.
Thanks.
Yeah, for those who were there, that statement was proved in Momchil Konstantinov's talk a year ago. Okay, but then so much about graphs. Then let's look at some manifolds. And let's talk about these gauge equivariant convolutions and gauge invariant convolutions. So yeah, to start with, we need to know what a holonomy group is. And here comes the hand-wavy definition of that. So if you take a point P in your manifold, then you can define the holonomy group at P. And it's defined to be the collection of all parallel transports. P gamma is the parallel transport along a curve gamma, which starts in P and ends in P. And it's a lemma that the parallel transport is actually always an element in SO TPM, special orthogonal transformation. And a second lemma that actually your holonomy group doesn't depend on the choice of basis point if your manifold is connected, which we always secretly assume. So whole P and whole P prime are isomorphic as groups. And so some examples, and one of the examples we're going to need later are the following. So the first example is the two-sphere, and we already know the holonomy must be contained in SO2. And actually, so the claim is for the two-sphere, the holonomy is equal to SO2. And you can see that kind of from the picture. Say you start at the North Pole and you fix the vector pointing in some direction, and then you go down to the point P, parallel transporting your vector. Then you go to the point C, always parallel transporting, and then you go back to the North Pole. Then you notice that like your vector changed a bit. And how much your vector changed depends on how long, like how far are B and C from each other. And in fact, by changing this distance, you can get a rotation by any angle you want. So you sweep out the whole SO2. Sorry, I need to drink a sip. Yeah, so that's S2 for you. Second example, the torus, the two torus. So that's the unit square with opposite sides identified. But if you take some curve like this blue guy here, in every point of the curve, the tangent space of the torus is canonically identified with R2. And if you, it's a calculation you have to make, but if you make the calculation, then you see that the parallel transport of some fixed vector is actually given by just leaving it the same in every tangent space. So that means the holonomy of this thing here, of this two torus, is just the identity, just one element. And now you're at an advantage if you don't know Berger's classification of holonomy groups, because if you do know it, you may think, oh, there may be no other options. If you don't know it, then of course you can imagine many other options. For example, this guy here, the icosahedron. This, I mean, it's not really a smooth manifold, but you can still define a holonomy, and you will find that the holonomy of this thing is Z6. So Z6 embedded in SO2 by subsequent rotations of 60 degrees. So for example, if you start, actually, I don't know if you can see my mouse cursor, probably not. But if you start on one of these facets and walk around the vertex, then you will notice that your vector has been rotated by 60 degrees. And it's kind of impossible to see, I think, in this picture, but if you print out a net of your icosahedron, then you will notice that. Okay, yeah, I mean, that's just the pre-waffle, that's just holonomy groups. But now that we have this, we can make the first little definition. We can define gauge invariant convolution. And that's defined as follows. So fix some point in your manifold, and then we want to define a convolution between F, which is a map from M to R, and G, which is a map on R2. And to do that, you fix some identification of TPM with R2. And now if you take any point P prime in M, now I want to transport the map G to be a map on the tangent space at P prime. And I mean, there's not much you can do. The way you do it is choose some curve from P prime to P called gamma. Then you have the parallel transport along gamma, and you can write down this map here, G P prime. So first it transports from one tangent space to the other, then it uses this identification F, and then it applies G. And what you get is a map from the tangent space at P prime to R, oops, not to R2, but to R actually. So the last thing is G, so it gives you something real valued. And then you can define, well, define is maybe a bit strong, but you can write down this line here, F star G at P prime is defined to be the convolution of the pullback of F. So pulled back to the tangent space T P prime M, convolved with just with this G P prime thing, and evaluated at 0. But of course, you see, we made a choice here. We choose this curve gamma, which connects P prime and P, and this expression is only well defined if the map G that we began with is invariant under the action of the holonomy group, which is a fun exercise to do, because if you choose another curve, gamma prime or something like that, then the two different parallel transports, they exactly differ by an element of your holonomy group. Yeah, so that's why it's called gauge invariant convolution. You can't convolve everything, you must restrict yourself to these nice functions G. Does that make sense? Any comments or questions on the gauge invariant convolution?
Does it depend on this big F? Or
yeah, I guess technically it does. Where does it? I would think yes. I would think it does. But once you parameterize your G by something, then by choosing different parameters, you can, so different choices of F can be offset by different choices of parameters for your function G.
Couldn't you also just say that G is a map from the tangent bundle to R? And then there's a
tangent bundle.
Yeah. Or for one point from just from the tangent space at P. Because the holonomy group naturally acts on this tangent space, and then you just require its invariant under this action.
Yeah, fair enough. I mean, if you have, yeah, that would probably be a bit smarter. The second thing that you said, to define G to be a map from TPM to R. It's true, the first thing that you said would be mathematically very nice if you say G is a map from the tangent bundle to R. But the problem is it's not obvious how you would parameterize such a function.
Yeah, for like something you want to feed into the algorithm, into a network.
Yeah, so that's the part I'm not talking about at this point. But if you parameterize your function G by some thetas, and then you want to minimize over these thetas and minimize some error and so on and so forth, yeah, it's not clear how you would parameterize a function defined on the tangent bundle.
Yeah, I guess at the end you always have to choose some kind of trivialization, but it's probably the later you have to do it, the better.
Yeah, or do you? Because like the gauge equivariant convolution is kind of doing exactly that. But let's
Wow,
get
can't
to it when
wait.
we get to that. Okay, so let's think about the gauge equivariant convolution a bit. So that's it.
Sorry, Daniel, can I ask
yeah.
you a short question? I mean, there is a question in the chat. Maybe you can see it because usually if you're
yeah, sorry, I cannot see that.
The question is, should you identify the tangent space TPM with R2 by an orthonormal basis or just randomly? So should it be like an isometry or just any linear isomorphism? Or is it important?
I mean, you can do either. Like you can, it makes sense to write it down even if it's not an isometry. I don't know. I have a feeling it would work better numerically later if you choose an isometry, but yeah, I think it should be fine.
Okay.
So what? I now do read the chat. Yeah, fair enough. I mean, you're right. The outcome will change depending on what f you choose and if you choose an isometry or not. But it doesn't really matter because in the end, so you fix your f first, and then you have your g, which is parameterized by some parameters, and then you want to find a minimum of some error functional. And I mean, yeah, it shouldn't really matter what you chose in the first step because you have so many parameters to minimize over. I think in the end, the algorithm won't really care what your f was.
I think if you choose a non-isometric f, you will just have a funny action of SO2 on R2, right?
Yes.
And that is a bit annoying.
Yes, that's, yeah, okay. I mean, I should have gotten rid of all these R2s, really. But I mean, what you say, what all of you say is true, yeah. Okay. So then let's have a look at this gauge equivariant convolution. So that's the last thing for today. You almost made it. And I only talk about this icosahedron because that's what they talked about in their paper, but you can do it for any G structure on any manifold if you wanted to. But you can imagine if you want to discretize something and then do machine learning, maybe it's nice to have some Platonic solid. So as I said, in this case, we have that the holonomy group is Z6. So by some general principal bundle theory, if the holonomy group is Z6, that means there exists a reduction of the frame bundle to this structure group. So the frame bundle is the set of all isomorphisms from R2 to one of the tangent spaces. So for each point, you have a bunch of isomorphisms, and then you throw all of these isomorphisms together, then you get the frame bundle. And a reduction is just a subset Q, which is a Z6 bundle. And so for our group Z6, we have a bunch of representations, and one representation we have in particular is the one which acts on R6 by permutation of coordinates. So yeah, every element in Z6 gives me an element in GL6 this way. And now what you can do if you want, you have your principal bundle Q, you have your representation rho, so you can write down an associated bundle Q times R6 modulo this representation rho. Yeah. So I didn't write down what's the definition of associated bundle. I mean, if you haven't seen it before, it's probably difficult to process when you see it now, but you kind of see the definition here in the next line. So because there I say a section of this associated bundle, so a map F from M to E locally looks like this. It's a tuple phi comma F, where phi is a map into Q, F is a map into R6, but because it's intertwined by this representation rho, or it's modded out by this action of rho, you have that phi comma F is literally the same element as if you multiply with these G inverses and Gs. But now what you can do is, now I can define a convolution. And first I define a convolution between some function h and the capital F, and then we use it to get a convolution of h and little f. So the convolution of h and capital F is defined like this. It depends on the phi, and it's an integral over TPM. And the one part is easy. That's again the pullback of capital F. So F was a function on M, pulled back its function on the tangent space, takes values in R6. And the other thing is H composed with phi inverse. So phi is always some isomorphism between tangent space and R2. So phi inverse maps into R2, then we can apply H, we get an endomorphism of R6. So this dot here in this integral, that's matrix multiplication of our matrix and our vector in R6. And now that we have that, we can write down the following convolution. We can write H star little f is phi comma, and then the convolution with capital F that I said before. But you see here on the left-hand side, this H star little f, there I don't have any dependent on phi anymore. And for this to really be independent of phi, I must ask for some transformation law to hold. And if you like trace through all these definitions, I mean, the proof is trivial once you work through these heaps of notation. But if you do that, you find this guy is well defined if and only if this equation holds. I won't read it out, but h of gz equals blah, blah, blah. Where here gz acts through the action of the holonomy group, and on the right-hand side acts through this action of rho. So yeah, so that way we can convolve functions on M with values in this associated bundle with these functions defined on R2. So it's a bit more complicated, and it's not clear at all how you would feed this into a computer now, because I mean, what does that even mean? An E-valued function is a bit annoying, but you can do it, and it works very well in some example problems. So the problems they treated with that is they took weather data from the sphere, for example, which is particularly nice because they have a wind speed, which takes values in some associated bundle, the tangent bundle, and yeah, then they have a bunch of convolutional layers like this, and with some fully connected layers, and outperform some other methods. Right, okay, so that's basically the end of the mathematics. Then I have one more thing to say before I close, and it's like a tiny recap. Yeah, sorry.
Yeah, okay. How do you compute this H convolved with big F at say a vertex of your polyhedra?
Yeah, let's not do that.
Oh, okay. So you just okay.
I mean, you know, I mean, if you were a mathematician, you would just compute in all the facets and then say, oh, it must be some continuous function or so. And so by continuity, you get it on the edges.
Oh, so it is a continuous function. Okay. Okay. Yeah. If you, yeah.
But like, if you're a computer scientist, you don't care anyway. You just want, like, you choose a bunch of pixels on your facets, and you just want to evaluate it on those pixels. Or I said pixels, points is probably a better word.
Okay. Well, what I don't understand is like how you go from, okay, you have a sphere, yeah, and some weather data on a sphere. How you go to these icosahedron or whatever it is?
I mean, for a scalar signal, is that okay for you? Like if you have a real valued function on the sphere, how you go to a real valued function on the icosahedron?
Yeah. Okay. Yeah, but why would I mean, like, what's?
Well, I mean, it's something that people really struggle with to do any machine learning with these data that comes from some spherical stuff.
So like, I'm not satisfied with a function on the sphere itself because, well, then I would need my thing that I convolve to be SO2 invariant, and that's too restrictive. So I want, like, I will lose every data about the direction. So I do something.
No, you don't. Even if you're literally on the sphere, you don't need your filter H. You don't need this to be SO2 invariant. You need it to satisfy this equation here. But if say your input is a function like a section of the tangent bundle, and your output will be a function of the tangent bundle, or like this bundle E here. Or, no, we're on a sphere. Let's say we want to go from the tangent bundle to the tangent bundle. Then there are choices of H which are not SO2 invariant but satisfy this equation here.
Okay. Mm-hmm.
Yeah, I mean that's what they do in the paper. So like if you, can't say a simple example saying, oh, just do this, and you immediately see this gives you more than just the invariant ones, but that would be something you could look up if you wanted to. Okay, let me wrap up. I wanted to summarize one thing and state one question. So if we're on T2, I define a bunch of convolutions, and they're basically all the same. So the smooth convolution and the gauge invariant convolution and the gauge equivariant convolution, if you chase through all these definitions, they all turn out to be literally the same thing. And two statements I made earlier is, so first, the smooth convolution, if you discretize it, you end up with this neural network convolution, the thing with the matrices. And in the limit, that's the same as the spectral graph convolution. Did I say that actually? Oh, maybe that wasn't stated, but it's, yeah, that was I did say that. That was one of the lemmas. Okay, but the thing is now, if you're on a general manifold M, the smooth convolution is a priori not defined. The neural network convolution doesn't make sense either, but you still have these other three guys. You still have the gauge invariant convolution, which is a special case of the equivariant convolution in like a particular sense. But it's not clear at all how that's related to the spectral graph convolution. So it would be nice to have some result like the complicated theorem that I mentioned earlier, where you say, oh, we choose some graph embedded in our manifold, and then you want that these operations commute to go from a manifold function to a function on the graph, then doing the spectral graph convolution should be the same as doing the gauge equivariant convolution and then restricting to a function defined on the graph. But that, I mean, getting the correct statement, that's probably the hardest part of the work here. So that's something you can think about in your free time if you want. And that's all I had to say. So thank you very much for listening.
All right, thanks, Daniel, everyone. Does anyone have any questions?
So for that final question mark that you had there, can you say something like in the case that you had with the icosahedron, if you choose your graph to be the obvious one skeleton of the icosahedron or dual to that or something like that, can you say something about that question mark?
So I can't, but that probably would make for an easier statement, at least, because then you don't have to say something about randomly choosing a graph and P almost surely, but you can say I take the one skeleton and then take some subdivisions, barycentric subdivisions or so. Yeah, it's a nice idea. I think that would probably be an easier statement to prove than the most general statement, but I can't say anything useful.
All right, any more questions?
So in this gauge equivariant convolution paper you read, is the weather the only application they do?
No, they have one more application where they actually they have two more, but one is pretty silly. But the reasonable application is where they take spherical photos, I think. So like a 360 degrees camera, and then you want to do some image classification or segmentation or so. I don't exactly know what they did, but something with these photos. And the silly example, I can also say it just for fun, is they take MNIST, which are these handwritten digits, and project it onto a sphere under some projection. And then they want to classify digits on the sphere, but then project it one step more to the icosahedron.
Yeah, that is a bit silly, but thanks.